right. So now models. So economic models, right? We don't come up with them just for funsies or because we think they're clever and fun to look at. We come up with economic models because they give us ways to think about the real world. And for what it's worth, we already have some results, right? We care about economic models because they give us results that are testable in the real world. And we actually already have some results from the SIR model, namely that the number of susceptible people in a population is going to be increasing as the in how quickly people are leaving the infected group, and decreasing in how contagious the disease is, right? So the more contagious the disease is, the fewer susceptible people there are, because more people will get the disease earlier because it's more contagious. And the faster people are leaving the infected pool, the more people will be susceptible because you're less likely to get a disease if it's less prevalent, right? And if people leave the infected pool very quickly, they don't have a lot of opportunity to infect other people, right? So now let's look at another implication of the model, which is what happens if we change the price of a vaccine, right? So you may remember that vaccination rate is equal to some function v of the price and how prevalent the disease is. So people get more of the vaccine when it's cheap, they get less of the vaccine when it's expensive, and right, so dv dp is less than 0, and dv di is greater than 0, right? So people get more of the vaccine. People are more likely to get the vaccine when it's very common, right? So none of us get vaccinated against smallpox because it's been eradicated. But if smallpox were still around, we would get vaccinated for it. And we'd actually, as smallpox became more common, we would get vaccinated very, very quickly because, as we'll discuss, smallpox is a terrible disease. There are people who think it is largely responsible for the depopulation of North America as sort of white settlers moved west, as well as the collapse of some of the big empires in South America, the Aztec and especially the Incan Empire. People think that collapsed due to basically the entire noble caste being, or half the noble caste, literally, maybe more than that, dying from smallpox. Smallpox was terrible. I've seen some estimates that I don't quite buy, but I've seen estimates that it killed as many as half of people who have ever lived died from smallpox, right? It kills a lot of kids and children. Smallpox is terrible, so if that came back, we would get vaccinated real quick against it. Right, but the idea is that V is going to be decreasing in price, so the more people get, the higher the prices, the fewer people get vaccinated, and increasing in the prevalence of the disease, so the more infected people there are, the more likely people are to get vaccinated, right? And so when we take the derivative of I star, it turns out that it's actually pretty difficult to solve for I star. But you can still take the derivative of I star with respect to the price of vaccines, and that's actually relatively easy to calculate. And after some math and some rearranging and some clever use of, some higher level theorems, like you probably need to use the implicit function theorem, things like that, stuff that we don't expect you to know, so just know this result, that in the SIR model, dIdP is negative, dV dP divided by beta plus dV di star, right? And so something you'll notice is that beta is positive, dV di star is positive, and dV dP is negative, right? That's because the contagiousness is always positive. Diseases can't be negatively contagious. People get more vaccinated as the disease is more prevalent, right? Vaccination rates rise as the disease is more prevalent, so this is positive. This is negative because people get fewer vaccines as the price of vaccines rise, and there's a negative sign here. So we have negative, negative, positive, positive, which leads us to say that this is greater than 0. So the number of infected people in steady state will go up as the price of vaccines rises, right? So this indicates, a vaccine subsidy is likely to be effective, right? Right. Vaccine subsidy will decrease prevalence in steady state. Now that might seem obvious, but oftentimes when you do these models and you think through things really carefully, things that seem obvious turn out not to be true. So for instance, I'll give you an example. You might think that, this is from my research, intergenerational mobility, which is sort of the correlation between your income and your parents' income, right? Or the inverse of that, right? It's sort of how so intergenerational mobility, which is sort of the odds you move up the income spectrum, right? It's one way to think about it. It's the odds you're born poor but end up rich or end up middle class, right? It's upward mobility. You might think that that's going to be if there's an increase in economic opportunity. For instance, if we increase education available to people from low income backgrounds, that's going to increase intergenerational mobility. That when you do these sorts of models, there are actually, in the last few years, there have been several models that have come out that people say, actually, that's not true, right? That the theoretical link between intergenerational mobility and equality of opportunity is much more tenuous than you'd want it to believe, right? There was a paper that came out in one of the best journals of economics recently that showed that that sort of these behaviors can move really weird. I have sort of a follow-on paper to that. You can see it on my website if you're curious. It's not particularly well written. I need to edit it to make it better. But I have a follow-up paper that's sort of just an addendum to that says, by the way, it's even weirder and less. I won't go into the details, but I enhance their findings and I say, actually, you can say even stronger things than they can. Their finding is actually too weak, and actually the link between intergenerational mobility and equality of opportunity is even weaker than you might than you might suspect. So the result that as vaccine subsidy will increase prevalence of a disease in steady state is actually not a trivial result, even if it seems obvious, right? Oftentimes when you do these models, it turns out what you think is obvious is not obvious, right? And that it may not be true. So that's one result immediately. That seems very obvious, but isn't that? But the form of the solution also gives some additional insights. So also, but it doesn't just tell us that the subsidy will be effective. It tells us under what circumstances the subsidy will be more or less effective. So, also, subsidy will be more effective if vaccine demand is price elastic, right? So the more people respond to the price of the vaccine, the more effective the subsidy will be. That makes sense. That should make sense intuitively, right? If people don't respond to the price of the vaccine, then a subsidy, if people don't get vaccinated more when the vaccine gets cheaper, then subsidizing the vaccine won't be very effective. But you can see that very clearly from this term here, where sort of the larger this term is in absolute value, the more elastic the more the infected population will change as you decrease the price of the vaccine in steady state. A subsidy will also be more effective if infectivity is low. Now this is less obvious, right? If I were to ask you, right, I before doing the math here, if you had asked me, will a oh, that's a terrible just parentheses with beta. Let me redo that. This is a non-trivial result. This is something that would not be obvious to me before doing the math here, right? So if infectivity is low, right? So if the disease is less contagious, then the subsidy will matter more, right? That is not intuitive. But why is that? It's because if the infectivity is low, right, that means that there are more susceptible people, and so it's more important to reach them through vaccines. If infectivity is high, a lot of them have already gotten the disease, so subsidizing the vaccine will be less effective because people are more likely to get the disease just through natural causes, just through like interacting with other people. But if infectivity is low, then the vaccine channel of moving people to recovery becomes more important. And so if infectivity is low, a subsidy for the vaccine will actually be more effective at decreasing the number of infected people. And then the last is if the vaccine subsidy will be more effective if the prevalence elasticity is low. And this in some ways is the most important result of the model, right? And this is the prevalence elasticity, right? This is how vaccination rate change with respect to infection rate. This says that a vaccine is going to be more effective if if people continue to get vaccinated, even if the disease is rare, right? And this, this is maybe actually the most important result of the model, because this is going to say, hey, this means that some diseases are going to be really hard to eradicate, because as infectivity, right, as I star gets low, as the prevalence gets low, people are less likely to get vaccinated because, you know, it's not as, they don't need to take the same, you don't need to protect yourself as strongly when the disease is rarer, because you're less likely to encounter someone who has it. And so you're less likely to, you know, get it from them. But that the vaccine subsidy is going to be more effective when the prevalence elasticity is low, right? And that's because you're not going to get like a feedback effect where, oh, okay, more people get vaccinated, and so that's going to reduce the number of infected people, which in turn reduces the demand for vaccines, right? What this result says is that the more we restrict that loop, so that when the prevalence elasticity is low, and so when people continue to get vaccinated even when the disease is rare, right? That's going to make subsidies more effective. That's going to be very important in the next section where we talk about disease control. But if you have been, this lecture, you have been looking on terror and with fear upon my, terror and despair upon my handwriting, this is the SIR model printed out in, more legible printed terms, right? So if you want to, copy down a more legible copy for your notes, you can find it here. And then lastly, this is going back to that sort of cycle of how economists think about diseases and disease and sort of the disease cycle and protection, right? So a vaccine subsidy causes more protection, right? Which is going to cause less disease. And a key point to seeing how much less disease it causes over the long term is how do people respond when there's less protection, right? So if we go back, this is the prevalence elasticity being low point. If people respond to less protection by less disease, by having more protection, right? This link here, right? So this arrow here is really key. And this arrow, the strength of that arrow is the prevalence elasticity. that's a terrible elasticity. Elasticity. Right, so the prevalence elasticity is this arrow here. Um, and so, right, what does a vaccine subsidy do? Right, it causes more protection, which is going to cause there to be less disease. How effective this is in the long run in terms of reducing the overall amount of disease that exists in this total cycle is how strong this arrow here. How much does less disease cause people to get less protection, right? How much does, like, when the disease becomes rarer, how many people don't get vaccinated when the disease becomes rarer, right? And that's the prevalence elasticity, and in this diagram it's represented by how strong that arrow is here. And so this connection is key for understanding economic epidemiology and why diseases can be so hard to eradicate, because once diseases become very rare, people don't take a lot of steps to protect themselves, which, gives the opportunity for the disease to make a comeback. And we'll go over that in depth up next.